All right, good morning. Can everyone hear me? People at the back, maybe give me a thumbs up if you can hear me. Yeah, great. So, yeah, this is kind of a difficult task because it's 9 in the morning and you guys all had the day off. And so now I have to somehow wake you up and get you excited. But that's easy, right? Because you spent the whole week eating that fatty cake that is unsupervised learning and supervised learning. And now we get the cherry, which is, the best part of the cake anyway. A little bit of rumble, laugh, slow, I'm going to warm you up. So this is going to be a crash course in reinforcement learning, so I'm going to try to keep it interactive. Going to try to go over what I think are the main pieces of the puzzle and kind of set you up for the rest of the week. So what is reinforcement learning? So reinforcement learning is all about agent-oriented learning, right? So agents that are interacting with the world to achieve a goal. That's the really fundamental headline thing here. They learn through trial and error interaction. So just like people do, just like animals do, they try stuff in the world, they see what happens, and then they try to learn from that. And they're going to get this evaluative feedback. They're going to get a reward signal. We're not going to teach them in the classic sense of telling them what to do. We're just going to give them feedback. And we like to say that it's the kind of machine learning that's very much like natural learning. And it's the key thing is the system has to figure out for itself, what's right or wrong based on the reward signal. So today, the goal is really, really simple. Try to wake you up, try to get you excited to set up the rest of the day, and really introduce your RL and sequential decision making and make you really comfortable with it so that you have the basic, foundations, concepts, notations so that you can understand and appreciate the rest of the amazing talks we have. And, that's the main goal here is to set you up for these advanced topics. So we're going to go through the basics of RL. There's going to be basically 3 parts to this. The basics of RL, states, actions, reward, time, NDPs, values, all the essential, most important things. We can't leave out any of these things. They're all super fundamental, whether you're doing, your first grid rule in reinforcement learning or you're trying to build this deep learning system that can play against humans in some game. You need all these things. We're going to take a deep dive into Q-learning to try to ground out these concepts and make them more clear. And then we're going to talk about what it means to go to function approximation reinforcement learning. And again, this is week 2, so you guys are already experts in learning parameterized functions, and so we'll just be putting these 2 concepts together. And throughout, I won't be able to hold myself back to talk about open research challenges and try to get you guys excited about learning in the real world because we've had so many successes, but this is the big frontier of reinforced learning research. I'm going to try to get you excited about that along the way. So there are many different ways we can learn about reinforcement learning. So Rich and Andy have made the 2nd edition of the book. It's amazing. So I don't know how many of you got to read the 1st edition of the book, or at least look through it? Hands up. And how many of you looked at the new edition of the book? Even more. That's great. So this, like I said, is free online. It's really, really wonderful. The first book was this beautiful piece of art that was just wonderful to read and explain really complicated topics in a very understandable way. You can just think of this as a refinement of that and then like doubling the content. So it really takes you from the first steps of RL, which I'm going to cover today, all the way to the burning frontiers of research. And of course, if you haven't heard about it, Martha, myself, and a huge team of people at the University of Alberta has made a 4-course specialization with Coursera about reinforcement learning. Course 1 has launched. It's going to cover a lot of the things we do today. In fact, a lot of the slides today are going to be a snapshot into what happens in the MOOC. So go check that out. It's got amazing notebook assignments. The last course is going to be a capstone where you implement your own reinforcement learning system. I think it's really just a great way to learn about reinforcement learning. So I think reinforcement learning is special, and I hope you all do too. And it's special because it has these really important key characteristics. And I'm going to kind of use this as a roadmap to go throughout the day. So it's going to organize this lecture. It's going to organize our thinking about it, and we're going to see how these characteristics interact with the problem formulation and the solution methods that we discuss. So, evaluative feedback, reward, right? Like I said, we're not telling the agent the answers. They get reward. They have to learn from that and figure it out on their own. Delayed consequence is also another really big one. It's not just you do something and you get the immediate feedback. You might do something, and then much later on you figure out how good that thing was, and then you have to kind of work backwards and assign credit in the right way to figure out which actions caused that outcome, and then learn from that. It's associative. We have to associate reward to different situations. Doing one action in one situation is very different than doing it in another, so we have to figure that out. That's what our learning algorithms have to do. And this one's a really big feature, online and incremental learning. It's become much more of a big deal in supervised learning and training neural networks, but this has been long-standing. A big characteristic of reinforced learning is that when we take actions, things happen, and we want to learn as soon as those things happen. That's the most direct way to learn, and there are a lot of advantages to doing that. And I kind of jumped to the bottom. Non-stationarity is related to that, but I put it as its own bullet because it's an essential feature of the problem to me. Learning is never done. The world continually changes. The agent changes. The way I like to think about it is we do a lot of work in robotics here, and just think about a robot driving around. You have your robot, you build it, maybe it has tires to drive around on, and then over time, those tires deflate, or other physical aspects of the system change. And so learning has to adapt to that. You can't just assume the robot is going to drive the exact same way all the time. So the world really is non-stationary, and we really have to build that into our algorithms to deal with it. And just like we started with, we need to do trial and error learning. We need to figure out on our own what's best. Because reinforcement learning agents typically are not given training data. They have to produce their own training data, and so how well you explore the world is going to determine how good your system does. So we're going to start off with a game to kind of let you see some of these concepts right away. So I'm going to go to it on my screen, but you feel free to go to the URL if you want. I guess it would be pretty hard to catch that URL, so I guess I'm going to go so fast that you won't actually be able to do it yourself. So you should be able to see it on the screen, and now I just have to figure out where my mouse is. Okay, so we got a game here. This is a multi-arm bandit problem. There's 3 arms here. And so what we want to do is we want to figure out which one of these buttons produces the most reward. Okay? And so what we're going to do is we're going to click on the buttons. They're going to give us a reward number. And your job is to figure out which button we should press next, because we want to find the button that if you pressed it forever, it would give the highest reward on average. Okay, so I'm just going to do whatever you guys say. So what button should I press first? Middle button. Click. Okay, give it 15. Now what? See, there's this camera right first, whatever. You can say outsides or insides. Okay, so we got a 15, we got a 9. What should we do now? Maybe press the other button we haven't pressed yet? Seems like a pretty solid strategy. 4. Okay, so now what do we want to do? Back to the middle. You guys are hungry for more reward. Another 15. Should we keep going the middle? Okay, I'll do middle. Okay, you have to be really loud if you want me to do something. It's pretty disappointing, guys. Let's try this one. Wow, 4, 4. Okay, so which one do you think is the best? Yeah, you're right. So when you're playing this game, there's a lot of questions you can ask yourself. Like, how do you decide which arm to press next? And anyone want to tell me what their strategy for telling me what to do? Anyone?
Just evaluate which one is giving you the maximum amount of return.
Uh-huh.
And then if it continues to give you that return, that you're probably more likely to continue to choose it.
Yep.
But then you also want to explore outside that to see if there's any better returns on the other one.
This guy read the textbook.
Check them a few times.
So yeah, we got to balance figuring out what's happening along the way, looking at the rewards we're getting, maybe averaging them, and then picking the best. And so what's a good way to explore? Does anyone, if they were thinking about exploring, were they just randomly picking the next one? Anyone want to share their exploration policy, someone different? You're not allowed to answer, Chaba. Yeah?
1 out of 5 times, so every 5 actions that you take, one of them would be chosen.
And then so how do you pick, so let's say we were thinking one's the best, how did you pick amongst the other 2?
Just randomly.
Just randomly. Yeah, that sounds like exploration to me. Let's keep going. Yeah, so there's this interesting thing we're doing, which is we have to decide when to explore. And when we pick an exploration action, sometimes we'll get a lower reward. So we lost out in getting more reward than we could have. So that was an example of multi-arm bandit problem. I think Chaba will probably talk a little bit more about that today. And it's really important to us, and it's a reason why the textbook starts there, and it's a reason why the MOOC starts there, because it has a lot of the essential characteristics of reinforcement learning, and it's a really good way to get your mind into the sequential decision-making framework. And so, there's lots of fun things going on. We have reward evaluative feedback. You guys, when you're looking at the rewards going by, I don't think you were writing them down and then waiting till some other time to process them. You were kind of processing them on the fly. You were learning incrementally and online. And of course, we needed to care about exploration. So yeah, that's what Csaba's going to revel in the next lecture. And so let's just get right into what we call Markov decision process and the reinforced learning problem and see how it's related and different from bandits. So typically we have this usual picture here. Everyone draws it a little bit differently, but you have an agent and it's interacting with the world. So you guys were telling me your decisions about the bandit problem, and then the bandit problem represented the environment, okay? So this is the general reinforcement learning formalism. And these two things interact at discrete time steps. So every time step, the agent observes the state of the world. So in this case, we have a rabbit, and it's by a carrot and some broccoli, and there's a tiger over here. That represents the situation or the state that the agent is in. And we say that there's a finite set of states here, okay? And then the agent takes an action. So in this case, the rabbit moved over. And so again, we have a finite set of actions. And in this case, we use a special notation to note that we have a specific set of actions for each state sometimes. And then based partially on the agent's action and the internal dynamics of the environment, the agent transitions into a new state. So in this case, our rabbit is now in the situation where it went over to get the carrot. The carrot was amazing, so it produced a reward. It got a +10. And now it's in a new situation where it's by the tiger. And so this process just continues on and on and on. And so it sets up this kind of general temporal dynamic where we have a state at time t. We take an action at time t that emits a reward, a scalar real value reward number, and we end up in a new state st + 1. And of course, this process just continues on and on and on forever, generating this stream of experience where the agent is continually taking actions based on the state, and the dynamics of the environment make the environment change state and emit new rewards. So this is what we call a finite Markov decision process. So the environment is meant to be unknown, stochastic, and potentially very, very complex. And we're going to formalize this with the language of MDPs. So we say that we have a finite MDP simply if the set of states is finite, set of actions is finite, and the set of rewards are finite. Now, we can extend this formalism to other situations, but for the stuff we're going to talk about today, this is not really a restriction. These could be really large sets. Okay, and we also need some way to describe the transition dynamics. How did the environment go from one state to another based on the agent's action? So we're going to talk about a transition function that just tells us the probabilities of all the next possible states and next possible rewards, given that the agent is in some state and takes an action. And we also want the state to satisfy a Markov property. We're going to talk about that in a second. So this is the big technical thing we need to talk about. And it's really quite simple. So you can kind of think of this as a little diagram here. We have the state that the agent's in, and there's multiple possible actions that the agent can take in that state, and then each one of those actions could result in a different next state, S prime, and a different reward along the way. So we have a probability distribution to describe this, which is just simply telling us if we're in this state and we take this action, what's the distribution over next states and rewards that we can see. So this thing obviously has to satisfy some basic rules of probability. It's a function from states and rewards and next states and actions to probability 0, 1, and those have to sum to 1 for every state in action over all the possibilities. And so the other thing I mentioned, the Markov property, is pretty important. So remembering earlier states would not improve our predictions or actions about the future. So a lot of times people get caught up in this, that they think that the Markov property means that nothing is hidden from the agent. That's not true. So a good way to think about this is like poker. So in poker, the definition of the problem is you don't get to see the other people's cards. That does not make it non-Markov. When you think about the Markov property is relating to the fact that you might think that these probabilities might depend on the whole trajectory of experience. But the Markov property says all that matters is the state and action that you started in. So in poker, as long as you remember the cards everyone played, and as long as you remember all their bets, that's still Markov. It's not asking to see things that you never could have seen by the definition of the problem. So, and the way I like to think about this is a statement about the characteristics of the state. The state contains enough information that you don't need to remember previous states to do better. Okay, so we've got MDPs. We have a, yes? Yeah. So another really classic example of this is like physical systems. So like the cart pole system is a very famous classic control problem where you have this cart sliding back and forth on a track and it's trying to balance a pole. Okay? If you were to make a simulation, you could set that up in a Markov way that the current angle and angular velocity of the pole would be enough. But in reality, if you remember previous angles and previous angular velocities, you can infer more about the actual physical dynamics, because the physical dynamics will be governed by something much more complicated, like, you know, if there's ball bearings in the system, the temperature of those ball bearings and how well they're sliding. And so physical systems are a classic case where if you remember previous states and actions, you can actually learn, or you can do better. And of course, you can always you could imagine something simple like a navigation task where you have to pick up a key. And if the state does not include the fact that you picked up the key, then you'd be non-Markov. Yep.
On the previous slide, P, the transition probability, you had also the reward as part of the matrix.
Yep.
For each action, you can get different rewards. So state.
Yeah, so it's a distribution over possible next states and possible rewards. Okay, so if you're in a state, you can take an action and there's a distribution of where you will end up and the rewards you could get. So the reward can be stochastic. Can somebody put your hand up so I can see who's saying? Great. Yeah. Can one state have many actions? So we're going to talk about policies in a second, and there's different policies that we can have. We can have deterministic and stochastic policies, and we'll talk about that. Any other questions? Yeah.
Can we, instead of calculating the reward, predicting it for the cases that we are not sure if there's going to be a reward or the reward is very sparse, kind of some way of...
So we haven't talked yet about predicting reward or what we might want to do with these numbers, and that's going to come right up next. And then, so if it doesn't clarify, you can ask your question then. Ready to move on? Great. So the goal of life, more reward. That's all we care about. Our agents, just like you guys playing the Bandit game, want to get as much reward as possible. So we want to maximize future total reward, and that's a pretty informal goal. So usually what we do is we calculate the scalar return. We call it the return. So we use GT. This is a real number, and what it is it's just the total rewards you see when you start in some state ST and you roll forward from the future. So it's always denoted by time, so we have a time subscript there. So it's saying, right now, if I follow my policy, what rewards will I see? So it's a trajectory of future rewards all added up. But there's a problem with this, right? What happens when you add like an infinite number of things up? Get some rumbles. So there's general unhappiness, but... So let's say I just add up, you know, an infinite number of 5s. Yeah, it's really bad when your like data structures that your system is using to make decisions is infinity. Like that's usually a problem. So, you know, the agent's interaction may never end, and that's usually the case I like to think about. We call them continuing tasks. So what we do is we discount future rewards. And you know, the basic idea is we multiply it by a small scalar gamma. And so gamma just gets raised to higher and higher powers. And of course, what is the effect of that? It says that the agent cares more about immediate rewards relative to much further delayed rewards. And of course, gamma can take any value between 0 and 1. And so this is what we call the discounted return. And it's just, you know, the exponential sum of these rewards that we see. So what is our goal? In each state, the agent should choose the action that results in the highest return in expectation, because, you know, the world's stochastic, it's noisy, so we always have to worry about things in expectation. Okay, so we're coming back to a roadmap here about the key characteristics of reinforced learning. And we've talked about MDPs, and so that gave us a way to kind of see how, in the problem definition, we're going to encode things like evaluative feedback, reward. We now have a problem formulation that describes how an agent gets rewards from its actions. And because we care about discounted return into the future, we have a way to reason about and describe delayed consequences and why they matter, right? So you can take actions now that might get you high reward, but that might put you in a state much later that you get lower reward. So you have to balance those two things. So we have to deal with these delayed consequences. But now we have to think about learning, we have to think about policies, we have to think about what we're going to do with this MDP formalism so we can do learning. So the first thing to consider is policies. So we're going to start with a really simple case of deterministic policies. So policy just maps the state to a single action. This is a deterministic policy, and we denote it with pi of s is equal to a. It's just literally saying, in this state, I'll take this action. That's all the policy is saying here. So to be fancy people, we usually use Greek letters because it makes us feel smart. And so you can think about an example of this here. You know, state S0, we take action 1. State S1, we take action 0. And state S2, we take action A0. So there's a couple things to notice. Here, you know, 2 states take the same action. That's totally OK. And in fact, in none of these states, anyone's taking this action. And again, that's completely legitimate. And so we can visualize this as a table to see those relationships more clearly. Any questions about deterministic policies? Okay. But stochastic policies are more interesting, right? We might do different things in the same state. We don't want to necessarily be restricted to, in this state, I always have to take this action. And people throughout the week are going to get more into why that's interesting, but there are many reasons in games where you're doing bluffing or when you have partial observability that stochastic policies can actually be better. So stochastic policy is a probability distribution over actions. It's saying, in this state, I have a distribution over which actions I'm going to take. So it might look something like this. This is a little bit weird, but this is the legend right here. And it's just saying that with high probability, I'm going to take the up action. And then very small probability, I'm going to take the down action. And then there's a little bit of probability of taking the right action. And so again, because this is distribution, it has to sum to 1 over the state, or over the actions in a state, and none of them can be negative. And so we can compare the policy in 2 different states, S0 and S1, and so they can disagree, but the important thing is that when you're using a learning system and has a stochastic policy, you sample actions from this probability distribution. So if you sample the policy in S0, you know, you're most likely going to get the up action, but you'll have a chance of getting all the different actions. And the other point of this diagram is to show you that the distribution can be very different in 2 different states. Okay? So, there are good policies and bad policies, valid policies and invalid policies. So let's just consider this really simple MDP here. So we have 1 state, and then we have 2 action choices, left and right. Okay? And so what's one stochastic policy we could have in this domain? It's a little test. Yes, sir? Always go right? Yep. What about a more stochastic one? 50-50. What a brilliant suggestion. Yeah, so you can just pick randomly in that state every time. That's totally a valid policy. What about this one? You gotta have your build. Alternate left and right. I heard a no. Someone's upset. I'm a little upset too. Pardon me? That's a deterministic policy, which is fine. But why is this an invalid policy? Yeah, what a monster I am. I told you that it had to depend on the state. The state was Markov, and then I introduced a policy here that depends on the previous action. So, you know, if that information is going to be useful to you, that should be included in your definition of the state. So we want to define our policies on states, not on other things like the last action or time or other things like that, unless it's part of your definition of the state. Yeah, these tests are really hard, but it is 9 in the morning, so. Okay, so we have policies, and policies are great because policies are telling our system what it's going to do in each state, what actions it's going to take. Now that we have policies, now that we have MDPs, we can talk about the thing we're actually going to learn, which of course is value functions. We're going to talk about action value functions today. There are lots of different value functions, and I'll tell you a little bit about them, but we're going to talk about the action value function. And the action value function is really, really simple. It says, what is the discounted sum of future rewards I'm going to see if I start in state S, I first take action A, and then forever after I follow policy pi? Okay? What is that in expectation? So if I did that many, many times, I start in this state, I always go forward, and then I follow my policy of run out of this room, and then I do that many, many times, starting in this state, taking this action, and running out of the room, what's going to be the discounted sum of future rewards if I average that? That's what the action value function tells you. We do a little bit of abusive notation here where we're saying that the expectation is defined over pi. Here we're just saying, just remember that this is a sequence and it depends on actions into the future, and those actions are coming from the policy pi. So this is the data structure telling us something about the long-term outcomes of what can happen if we run this policy. Now, another classic misunderstanding that people have is that they believe that somehow this action A must have a strong relationship with the policy pi that we're asking the question about. But that's not true. So policy pi may never take the up action, but you can ask the action value function, what would happen in this state if I went up and then followed this policy? And why would we want to do that? Why would we want to allow asking our action value function about actions that pi doesn't do? Any ideas? We want to use this thing to improve our policy, this data structure. So of course we're going to ask it things that the policy isn't currently doing. So that's really, really important. And so I always try to make value functions as exciting to you as they are to me. I think they're amazing. Think about what they allow you to do. The value function in this state is telling you something about the whole future of interaction with the system. It's saying, if I started in this state and I took an action and then followed the policy way into the future and then averaged those things, that's the information this thing holds. Right? It's caching all this future information into one number so that you can make a decision very efficiently. And of course, this number is going to have lots of stochasticity, right? There's going to be random choices of the policy. There's going to be random transition due to the environment dynamics. Maybe you try to run quickly on ice, but ice is slippery, so the run forward action doesn't succeed all the time. So there's stochasticity throughout all of this, and of course that's why we take the expectation to try to manage that stochasticity. Any questions about action value functions? Simple stuff. So, we have policies, we have value functions. Now we care about optimal policies. You guys are here to maximize reward. You're going to come eat the cherry. And so we want to learn optimal policies. So policy pi star, we call it pi star, that's how we denote the optimal policy, is optimal if it maximizes the action value function. So you can just literally think of the value function for the optimal policy, the action value function, is just taking the value function, the action value function for all possible policies, and then taking a max. The one that has the best value function is the optimal policy. And we usually denote that with Q star. So all optimal policies share the same optimal value function. That's what we call the value function for the optimal policy. And then if you have the optimal value function, Q star, it's really, really easy to act optimally. You just literally say in the state what gives the biggest value. So you take an argmax with respect to all the actions. And that's the beauty of value functions. If you could somehow figure out what this thing was, all you have to do is act perfectly greedy with respect to it. So we're using a myopic, one-step greedy routine with the data structure that caches long-term effects to act optimally. I think that's really beautiful. And there's always at least one deterministic optimal policy. So we're using the value function to order our policies. And so this is going to interact with a couple different things. Like, for instance, it's going to interact with the discount factor. So we'll play another game here. So we have an MDP here, and this MDP, sometimes I call it the butterfly MDP, sometimes I call it the potato. You have this state here, x, and you only have a decision really in x, right? In x, you could take action 1 or action 2. If you take A1, it gives you a +1 reward, and then you're down to state y, and then from state y, the action brings you back to state x with a reward of 0. A2 takes you to z, you get a 0 on the way, but you get this +2 on the return back to z. Okay? So obviously discounting is going to matter here. So we're going to consider two policies and try to think about which policy is optimal given different discount factors. So there's only one decision, so pi 1 just takes action 1 and pi 2 takes action 2. Okay? So sometimes this thing doesn't talk. So gamma 0. What does gamma 0 mean? You put your hand up. Thank you.
You only consider the reward for the next step.
You only care about the next step reward. You're totally myopic. You're like you're in the Bandit setting. You don't care about those future rewards. You say, if there's a chocolate bar on the ground that immediately leads to a tiger attack after that, I don't care. That chocolate bar is totally worth it. So, in this case, the value of this is just 1, right? It's just the discounted sum where the discount is 0, so 0, so that we just care about the very first reward. And what about for the other one? What's the value of pi 2 in this state? 0. So A1 looks pretty good. Okay. But now we're going to make it more complicated, and I'm going to try to get you guys to think about what the value would be for 0.9. So what would happen if we took A1 over and over and over? Well, we get a reward of 1, and then we get gamma to the 0 reward, and then we get gamma squared times 1, and then the 0 reward times the gamma cubed, and so on and so on and so on. So how do we compute this value? Anyone have an idea? Yeah, it's one of these fancy math series things. So we can write it this way. And the way you do that is you just look at all the things, and of course there's a bunch of things multiplied by 0, so you throw them in the garbage, and then you can write them as this sum. And the sum looks a little scary, but of course we have these classic rules about infinite series when they go from 0 to infinity of let's say x to the k. And so we can use that rule here because we can just think of the inside term, the gamma to the 2, as just the x variable. And so it ends up being 1 over 1 minus gamma squared. And so we get 5.3. And of course, we can do the same thing with the other policy. Which one do you think is going to be better? More mumbles. Pi 2. So we can do a similar thing, and in fact, we can make that sum look a lot like this one, and then you end up with something that's gamma over 1 minus gamma squared times 2, because we're getting a reward of 2 every time, not 1, and we get 9.5. So in this case, this is the better one. So this is just to show you that the choice of gamma, the horizon of optimization really, really matters in reinforcement learning. Any questions about that? Yeah. That's a great question. There are formalisms where the discount can actually be a function of state, so it can effectively change on every time step. That's not something I'm going to get into. I think maybe some of the later lectures might get into that, but you can do, so that's an exponential profile, and you can do all kinds of weird profiles. That's a great question. Yeah? So in this case, the world is stationary, but in general, it may not be. Yeah? We're going to talk about that, but in general, we're going to design. So in these MDPs we talk about, and like a lot of examples in the textbook and in the MOOC, we deal with stationary MDPs. But usually we design our algorithms not to exploit that too strongly, and we're going to see that in the next algorithm we get into. Okay? Yeah?
In this example, we designed the lambda to be very close to the reward of selecting I1, and therefore we are reducing this effect of selecting I1 over and over. But in real-world application, it might be much more complicated. Is this a general solution, or we are going to?
So this isn't the only solution. This is the classic solution that often makes the algorithms easier to analyze. And a lot of people like it because of the economic intuition that $1 today is worth more to you than $1 in a year or something like that. But there are all kinds of formalisms. So like I said, non-exponential profiles, you can have gamma change as a function of what state it is. And there's totally different formalisms that don't even use discounting at all. So we have average reward formalisms. So there's many different ways to model these problems. And what you do is you choose the formalism that best matches your application.
And for an example where you have like two possible policies to pick, one gives you a small reward, one gives you a very large reward. But if you do greedy, then you always are satisfied with the easy but small reward.
That's right. Yeah, so this is just meant to tickle your intuitions about how gamma interacts with policies and how to compute value functions and things like that. But this is very much an exercise. I don't usually think of problems of having, I have two policies and which one do I choose based on gamma. I'm thinking about learning systems, and they're going to learn their own policies. First, this person.
Who picks the discount factor in a problem?
God. I mean, it's part of the problem design. There are the formalism I mentioned where Doyne is going to talk about it later, where we do off-policy learning, I'll allude to a little bit today. Then you kind of push the specification of gamma into the agent. But for classic, optimal control problems like this, where you just have one source of reward and one learning agent, we usually think of gamma as part of the problem, but another formulation is part of the agent. Okay, one more and then.
Yeah, so could you go back to the last slide?
The last slide. This one?
Yeah, I don't understand the last point. Is that the general series?
There's always at least one deterministic optimal policy. Yep. That's true for finite MDPs. And so you can think about that as, imagine that you had two policies, maybe you had three policies, or you had two policies, one that was better in one part of the state space, and one that was better in another part of the state space. You could then make a new policy that does what the first one does in one part of the state space, and the second one does in the other part of the state space. Now, the proof of this is a little more complicated than that, and I can share resources on the Slack channel. There's a really nice book by Ross that goes through a lot of the theoretical results of MDPs, and it's actually like a really straightforward, easy to go through proof, but I'm not going to cover it today. Yeah.
So you're optimizing now for the optimal policy for this action value, right? So we solve the problem, but we already know the action value function from the beginning.
Yep, so this is all foundations, and we're going to talk about how you learn action value functions and interact with the world at the exact same time. Okay? So I'm excited. Let's move on. So what we just did was, like I said, very much an exercise. We had a really simple MDP that there were two deterministic policies. So we just brute force searched the space of possible policies, and then we just computed their value functions. Okay, there are various ways it can be value functions, but this would be a way to find optimal policies. But this is probably not the best idea, right? In a general MDP, there's an exponential number of deterministic policies, and so let's think of that strategy. We'll just enumerate every single possible policy, compute its value function, kind of like we did there, and then we'll just pick the one that has the best value function across the states. Simple. You can start now, and then by the end of the universe, I'll ask you how it's going. Even in small MDPs, this is not tractable. And then when you think of things like Go has a huge state space, more states, more configurations of the game than atoms in the known universe. We're not going to do this. So what we're going to do, we're going to do reinforced learning methods that are based on Bellman equations. Okay? So let's talk about one of those guys now. So MDPs have given us a language to think about and formalize evaluative feedback, delayed consequences, and policies and value functions have given us a way to think about associating different actions with different situations. So I've used problem formulations and data structures to talk about these first 3 points. And to cover the last 3 points, I want to talk about a really classic learning algorithm called Q-learning. And it's going to help us really make concrete online learning, trial and error exploration, and non-stationarity. And we're going to do it in a simple setting. We're going to do it in the tabular setting where we can write down that value function. We can put a value in a table for every single state, every state action pair. And this is just because it keeps the concept simple, and then we'll right away jump to function approximation. Okay, so we're just going to go right into it. This is the Q-learning algorithm. So tabular Q-learning algorithm. So we're going to have a step size parameter. I'm going to explain that in a second, an exploration parameter, epsilon. And then we're going to initialize a table of action values, QSA, one for every state in action, and we can do it arbitrarily. There are advantages to doing it different ways, and we'll talk a little bit about that. And then we're just going to interact with the world. So the world has to start somewhere. It has to start in some initial state. That's part of the problem design. And then we're just going to interact forever. So we're going to choose actions in our current state based on our policy. It might be something like epsilon greedy. We'll talk about that in a sec. But it's somehow related to our action value estimates. Okay? Going to take an action, observe the reward, and the next state. And then as soon as we have that data, we have all the things we need to make a Q-learning update. So we want to update this value function, right? We need to learn the value function, because if we had the value function, we know how to to act optimally. So it's a really simple update, and we'll talk about it in a second. And then you also have to remember the previous state, right? Because there's a state here and a state here, so we have to record that down in the agent. And the way I like to think about it is, the agent's somewhere in the world, it does an action, it ends up in a new state, it remembers where it was, and then it does an update for the value of the action that it started in. So it has a one-step memory. These are often called one-step methods. Okay, and then the update target is a little funny one. So this is like a classic, error reduction rule. We have our estimate of the values in state and action, and we're going to move that towards this error term. So we're going to move it a small fraction away with the step size. That's classic supervised learning type thing. And then we have the basic structure of our learning rule, which is the error is between our old estimate and this new target here. And this target looks a little funny. It takes into account the reward, and then gamma, and then the maximum value in the next state. Okay, we're going to unpack that though. So Q-learning, it's really, really amazing. It converges. This was proved a long time ago. We get long-term optimal behavior with no model of the world. So remember when we talked about MVPs, there was this transition function P that told us how the world interacted. We don't need to do that. We don't need to figure out what P is. We just need to interact with the world and then update our value function and then act really with respect to that, and we get the optimal policy in an MVP. So, bird's eye view overview, Q-learning, but how does it work? What are the guts of it? So one of the most important things about Q-learning is that it's online and incremental and how it achieves that. Okay? So you might think that we need to wait for a long sequence of rewards to be able to update our value function, right? It's defined on this infinite sum, this infinite discounted sum. But that's where the magic of bootstrapping comes in. So the key idea behind Q-learning and temporal difference learning methods in general, of which Q-learning is based, is that we're going to use an estimate of our value function to update our value function. We're going to update a guess from a guess. It's using its own learned values to make itself more correct. So what we do is you can think of it as we use a stand-in for the rest of the return. So if we just think of taking the first reward and then gamma out of the rest of the sequence, so we divide this whole thing by gamma, so we have a gamma in front, and then we have RT plus 2 times gamma RT plus 3 times gamma squared RT plus 4, and so on. That's just the action value one step into the future. So there's this recursive relationship defined by values and returns, and so that's what we're doing here. We're just updating towards this one-step thing. And that's why Q-learning is a one-step algorithm. It waits one step in the future and says, I'm going to look at the one reward that goes by, and then instead of waiting until the end, whenever that comes, I'm just going to say, well, what do I think the value is for the rest? Because that's what this thing is saying. It's saying, this is what I think the value in the next state is if I take a particular action. So it updates towards this one-step TD target. And of course, Q-learning had a max in its update, so it's actually updating based on the Spellman optimality equation, so we have a max here instead. So that's the one-step TD target. Yep?
So I'm super new to reinforcement learning.
Mm-hmm.
Like, what are some conditions under which there was like some theorem
Uh-huh.
on the previous slide that this converges?
Yeah, so there's lots of technical conditions. One of the conditions is this little step size parameter I talked about, which says how big the update to the value function is in every step. That has to satisfy certain criteria of basically going to 0 eventually, so you stop learning.
What about assumptions on the world?
So the assumptions in the world are that it's a finite MDP. Okay? And so what are the other assumptions? The other assumptions are that we have to visit every state and action infinitely often. We have to be in every state and try every action an infinite number of times. Of course, we're not going to do that with our algorithms, but that's so that we can say, with high probability where something converges. Yeah? So all of these things are expectations, so it's never about one trajectory. This data structure is talking about all the possible trajectories I could have from this starting point and what is their average. Okay, so I said that this was based on this thing called a Bellman equation. And Bellman equations are this thing that is a mathematical truth that you can derive from the definition of values and returns. And so it defines the relationship between value of a state and the value of the possible successor states. That was what we were doing in the Q-learning update. We were saying that the value of the state that I'm in right now is related to the reward I would get on this action and the value plus the value of the next state discounted. So there's some sort of relationship between those things. And that's exactly what the Bellman equation formalizes. So this is the Bellman equation for Q pi, and it's just saying the value of this state in action is related to the value of the next state in action conditioned on a bunch of probabilities, right? So we have to consider all the possible next states and rewards we can get to, and then that'll give us a reward, and then we have to consider all the possible actions that our current policy would do. And so there's a Bellman equation for V pi, which is something I haven't talked about yet, for V star, which is the optimal state value function, and for Q star, which is the optimal value function. So we have 4 Bellman equations, one for each one of these cases. And aside from being fun to write out a bunch of sums and looking really impressive, it's actually really important to reinforce learning. And so one of the quickest ways to understand this, and it's why it's one of the first solution methods we talk about in reinforced learning, is that dynamic programming algorithms in reinforcement learning you can think of as taking this Bellman equation and turning it into an iterative update to directly compute value functions in optimal policies. That's what dynamic programming does. It literally just turns this into an iterative computer program, which is fun, but we need this pesky model of the world, the transition dynamics thing here, right? So we need this guy. But reinforced learning methods are well thought of, so Q-learning, SARSA, temporal difference learning, all these methods are well thought of as trying to approximately solve the Bellman equations by just interacting with the world, just getting samples of the agent doing things in the world and seeing what happens. And so we usually call that model free. It doesn't need P at all. Okay. So the way we achieve online incremental updating when we want to learn about these delayed consequences things based on infinite sums is we use this idea of bootstrapping. Bootstrapping gives us a mechanism to update the value function on every single time step without having to wait all the way to the end. But just like you guys did in the Bandit problem, we can't just act greedily with respect to our value function. And why not? Well, there's this exploration exploitation problem. You can't choose the best action every single time. And there's a whole host of reasons why. For one, you're learning your values as you go. What if they're wrong? What if your current estimate of the value function is incorrect? Then, so maybe you took an action and you got lucky because the world was stochastic and you get like a plus 20 for taking one action. If you then forever on just take that plus 20 because it's better than the other action values, that might actually just been a random chance and it might have been really low. Just like we were playing the Bandit game, sometimes you get high rewards, sometimes you get low rewards. So it's important that you keep refining your estimates. And learning is never done, so they could continue to change. So we actually have to try all the actions many, many times. But you also can't explore forever, right? We care about getting reward now. So we have to balance exploring, picking what we think is the best with exploiting, or we have to exploit, pick what we think is the best, and balance it with exploring, which is trying to update our understanding of the world, trying to figure out which actions are best. And we have to do this in every single state that we could possibly be in. So how does Q-learning do this? Anyone have an idea? See, I'm doing bad for time, but I'd also like to point out that there's been lots of questions, which is good. Sorry, Cam. Guys, read the textbook. Yeah, so what we say about Q-learning, because Q-learning is not tied to this epsilon greedy algorithm. You can pick actions in any different way. The definition of Q-learning is not as restrictive as what the exploration policy is. So we choose actions in any way, perhaps based on our estimate of the value function, such that actions are taken in all states, infinitely in the limit. So one classic way to do this is epsilon greedy, and so we have some cute pictures here. So most of the time, with probably 1 minus epsilon, you do what you think is best. You ask your value function in this state, what's the best action? And I'm going to do that. Okay? So maybe that's the forward action for this ostrich. And then a small percentage of the time, you explore. and you just literally do something random. Okay, so maybe you go backwards or you turn the other way, you pick a random action. So Q-learning was doing that based on its action value function. And we've given this kind of exploration strategy maybe uncharitable name, but I think it's pretty accurate, which is we call it dithering or undirected. It's not reasoning very deeply about the world when it's exploring. For instance, what would happen if you've tried on previous experiences in this state to do some action and it was terrible? It was minus a million, okay? It was like coconut. I hate coconut. So I do this action of, come to this lecture theater, and every time I come to this lecture theater, people force me to eat coconut. I just hate it. It's horrible. But then my epsilon greedy policy is like, hey, maybe this morning I'll go to the lecture theater and have some coconut. That's stupid, right? Maybe we could do better by paying attention to the values and not just completely acting randomly. And of course, there are tons of other exploration strategies. One really simple one is optimistic initial values, which just means we can initialize Q in different ways to generate systematic exploration that slowly goes away over time. And the way to think about this is this ostrich in the beginning just thinks every action is amazing. Just walk around saying, oh, I bet going forward's awesome, going backward is amazing. It does all these things. But then, of course, it realizes through learning, this kind of sucks. There's just coconut everywhere. And so that's a very simple heuristic. It doesn't work quite as well with deep networks as it does in, say, linear or tabular case. And there are also very fancy ones like RMAX and model-based interval estimation. These require learning models of the world. Martha might talk a little bit about these later in the week, but there are more sophisticated things we can do, and this is a really open problem in reinforced learning. The textbook and the MOOC talk about simple exploration strategies because that's the thing we know best, and we need to work a lot harder on that. So the other thing the Q-learning is doing, which is really interesting, is off-policy learning. So off-policy learning is learning about one policy while following another policy, okay? And what does it mean to learn about a policy? Well, by that I mean literally like learn its value function, okay? So we have one policy we're learning about, and we have another policy that's actually making decisions in the world. That's what was happening with Q-learning. So Q-learning is off-policy because it's learning the value of its deterministic greedy policy, deterministically greedy with respect to its own estimate of the value function, and which gradually more and more becomes optimal as the value estimates converge, but it's generated by data by something like epsilon greedy, which is more exploratory. So there's two different policies. One that takes random actions every once in a while, but Q-learning is learning about the optimal greedy policy. So we call that off-policy. And it's really key for Q-learning's exploration strategy, but it's also really, really important in a bunch of other areas of reinforced learning, like batch reinforcement learning, learning from demonstration, parallel learning systems. You might want to learn many value functions in parallel, or many policies, or you might want to learn models of the world. These all typically make use of off-policy learning. Okay, I think I have to speed up a little bit here, but I want to just cover the last point in this section, which is just the last thing, the simple way the Q-learning deals with non-stationary. Yes, sir?
Why don't we have an important sampling correction term?
Good question, because Q-learning is updating with this max term, and so Q-learning has this crude way of achieving off-policy learning, which is basically it's updating towards the optimal value function, and it's just using the Bellman optimality equation. More generally, if you want to do other approaches like doing it in the non-control setting, usually we have, likelihood ratios, importance sampling ratios, and Doina's going to talk a lot more about that. So, non-stationarity, learning never ends. So how does Q-learning deal with this horrible problem? Like I said, our examples are stationary, but usually our algorithms are not. So how does Q-learning deal with this problem? Anyone? It's one letter on this screen. Alpha, right? It's making small updates on every time step. But what wouldn't work? Making alpha like 1 over t, so that it would slowly go down to 0. We want the step size to be a constant, or maybe change with time in a way that it doesn't get very small, because learning is never done. So as long as there's a constant step size here, that means it'll continue to update its action value estimates, which means it'll continue to refine its policy, even if the distribution of reward changes, even if the MVP has drifting dynamics, it'll account for all of that. Okay, I'm going to race into function approximation. So we've covered our key characteristics. And so the online incremental learning, that was all about bootstrapping. And the need for trial and error, we did that with off-policy learning and exploration exploitation. So can we do this all with function approximation? Well, of course, you guys are more pros about function approximation than I am because you spent the whole week, and I basically skipped all the lectures. I was very lazy. But there's some special things to talk about here. So of course, we can't just make, a Python array to hold every value in the universe. That's not a scalable approach, Sometimes the state space is way too large, like Go, I told you it's huge. Sometimes the state space is continuous. That means there's just an infinite state space. So we can't just store these individual values in tables. We're going to use parameterized functions, and we're going to frame value estimation as a supervised learning problem, which we will solve with gradient descent. But there's this new challenge, which of course is always a challenge when we turn to function approximation, which is generalization and discrimination. So function approximation with reinforced learning is actually really simple now that you have an idea of what value functions and policies and MDPs are. Instead of having a table, we're just going to use a parameterized function. So we're going to define a vector of weights, W, and that's going to define our value function approximation. It's going to be some parametric function. I'll give you some examples. And so basically the game is we use this estimate of the value function based on these weights. And what we're going to do, the game is that you adjust these weights up and down to try to make your estimate Q hat as close to the true thing as possible. Okay? So the approximator could be a neural network, where it's the parameters of the network are the weights. We could also just have a linear function of the features, so you just compute values by taking inner products. But it's important that this is computationally efficient. So usually we look for systems that scale linearly in the number of parameters because we don't want it to be some very expensive procedure just to ask what the value is. Because remember, Q-learning was doing that multiple times in every time step. So if we're creating a very expensive computation, that would be bad. And so we can do this with regular state action values or the optimal one. And so you can think about a neural network as doing this approximation. So we have this picture, which is the state. So it's maybe an image of a duck and an apple. And then so that passed into a neural network, and the weights of the network are the weight vector that I was talking about. And then the output of this network would just be the action values, the estimated action values for each one of the actions. And of course, you can do it slightly differently. You can pass in the action as an input to the neural network. So you pass in the state and the action, and then you just get out one thing that says, in this state and action, this is what I think the value is. So that's kind of two classic ways we do it with the neural network. And so this is where we get into generalization and discrimination and how it interacts and how to think about it in reinforcement learning. So generalization is a very, very key thing. It's about the efficiency of learning and reinforcement learning, which is we want to use updates to one state to affect the values of many, many other states. If there's a ton of states, in fact, there's so many states that will never see the same state twice. So we have to do things like imagine this value function here. We have some states and some actions, so we want to know the Q values. If we're in state S2, what we want to do is perhaps update the value of multiple states at once, okay? Because that's going to make learning more efficient. You can't visit all the states, so you have to say states that are similar have to share values so that I can update as quickly as possible. That's what generalization is about. And we have a little cartoon here. You can imagine a robot that's interacting with the world. It has some sensors, and it's trying to pick up cans, and so it really cares about the distance to these cans. Yeah? The data is created by the agent taking actions in the world. It creates its own data set. So we have this robot. He's interacting with the world, and he sees this can here. That is a specific situation based on the way this path curves, but we should really treat that the same as this one because the distance to the can is the same. And so in terms of value, even though the sensor readings in this robot might be different for these two situations, we will want to group these two situations together and say they should share the same value. And then there's another side to this coin, which is discrimination, which is we want to be able to say that the values of two different states are different in certain situations when the states are very different in terms of value. Okay, and so the cartoon for this one is maybe it's the same distance to the can, but there's a brick wall in the way, so the robot's going to have to drive around it, and maybe the robot doesn't have the best policy right now, so it might even bump into the wall a couple times. So these are very, very different situations. So we want to be able to discriminate these two states and learn different values for them. And so this kind of creates a 2D plot. So we have generalization on this axis and discrimination on this axis. And so there's a couple interesting points in this plot. One is tabular methods, very high discrimination, right? We learn a table value for every single state independently. So updating one table value does not affect the values of any of the other states, okay? But that also has low generalization. We can't take advantage of shared learning there. Another extreme is just treating all the states the same. No matter what happens in the world, no matter where you are, no matter what thing you do, you just get the same update. So that means you're just going to basically learn the expected return across the whole state space. Now, ideally, we'd want to be up here. Like, that's just the dream, right? High generalization, high discrimination. It means we're going to group things together and learn really quickly. Maybe I might say that the value in this open space down here is all similar, but maybe being in this seat versus being at the back are different values. We get to do that as well as humanly possible. That's kind of up there. But in reality, we're going to be somewhere down here, right, where we end up trading off generalization and discrimination. It's not always a trade-off, but that's often what happens. So that kind of leads to Q-learning with function approximation. It's actually really not that difficult. Basically, the algorithmic structure is the exact same. You have an exploration policy, you interact with the world, you take actions, you observe next rewards and states, and you do a one-line update on every time step. There's a couple special things here, but none of these things are special to you guys because of your last week's training, right? So maybe we have this loss function here, this objective for Q-learning. This is a very classic one, squared TDR. And then so we're going to do the Q-learning update with function approximation. This is what we usually do. We update the weights with alpha times the TDR from Q-learning, or the TDR from Q-learning, right? So we have this max target just like we had before, and then we're going to have the partial derivative of our value, right? That's just the regular gradient descent thing. When we want to do gradient descent on this objective, we're going to end up with a term that is the gradient of our value approximation in that state. So this is a vector the same size as the weight vector, and all it does is it just tells us which of the parameters to update based on the most recent transition to decide which one should get credit for the recent decision. But so this is a little bit weird when we think of like a gradient descent thing, because it's like when we did the derivation, we looked at this term and we said, well, there's a W in here, but what if W wasn't in there? What if we just pretend the gradient of that thing is 0? And that's if you start with an objective like this and you get to the Q-learning update, that's why we don't say the Q-learning is doing gradient descent. We call it a semi-gradient method, because it's like it's leaving out part of the gradient. So it means that this algorithm is fine, it's easy to implement, it works really well in practice. If you're doing this in TensorFlow, you'd put a stop gradient on this thing here. But it also means it's not a classic stochastic gradient descent algorithm, which means the analysis for Q-learning is involved and complicated because we can't just apply standard results. You know, people had to start a whole industry of analyzing Q-learning and TD methods because of this kind of thing. We don't really have an idea of what objective it's ascending on. We just have an idea of where it gets to. But so this choice can lead to instability, okay? And this is something that we've made a lot of progress on. That guy over there helped a lot, standing up on the side. Thanks, Chaba. There's a really, really perplexing problem because Q-learning can diverge. There's counterexamples that show Q-learning can explode. So the weights of the value function approximation can go to infinity. It's really bad in a learning system. But it's not because Q-learning is doing control. It's not because of exploration or greedification or sampling. And it's not even completely due to nonlinear function approximation like a neural net. It's really stunning. Dynamic programming methods can diverge with function approximation. The ones where we have access to the model of the world and you're using the Bellman equation over and over, that can diverge. And in fact, even TD, the algorithm that Q-learning is based on, so we're not doing control, we're just doing prediction, with linear function approximation can diverge. So we call that off-policy linear prediction case. That can diverge. This is really problematic. And what we say is it's due to this thing called the deadly triad. So it's three things that if we have them together can lead to instability. It's not a guarantee, it just means if you have these things, you should be a little worried. And so function approximation, you know, approximating the value function so we don't have a table. We're significantly generalizing over states. Off-policy learning, so this is the backup diagram in Q-learning. So if we're doing off-policy updates, so we're learning about one policy while following another. And bootstrapping, that thing that allowed us to make an update on every time step rather than waiting till the end. Updating our value function with our own estimate of the value function the next state. If you have these three things, you can have instability. And this is really frustrating because off-policy learning and function approximation are things we really want to do. We can't have giant tables. We need to do function approximation. That's like non-negotiable. But for me, off-policy learning is also non-negotiable because I want to learn not just one policy, I want to learn hundreds or thousands of policies, and I want to learn hundreds or thousands of value functions, so I need off-policy learning. That's going to help a lot with that. So those are non-negotiable to me. And a lot of us, that Sutton guy, he really likes bootstrapping, and I also like bootstrapping. It really makes our methods efficient. It helps us learn online. But there are people who are a little crazy, like Dale. And Dale was going to talk to you this week about, well, these are non-negotiable, but maybe we don't need to do the bootstrapping thing. And he's going to discuss a framework that gets for that. I don't like it, but it's really, really cool, and you should come check it out. So that's one way of dealing with the triad, right? There's also algorithmic solutions. So we now call them newish because they've been around for a while. This is something that Chaba helped a lot with. Gradient TD methods, basically defining a new objective function for TD methods and then trying to do stochastic gradient descent of those objectives. Produced a whole family of algorithms like TDC and GQ. Sridhar Mahadevan came up with these proximal gradient descent methods, which lead to some really nice analysis. And so it made it sound to do off-policy learning and function approximation. So we get to do bootstrapping because they're TD methods, off-policy learning, and function approximation, and it's okay. It converges. It doesn't explode. But if you just randomly poll people in the community, it's like, so how did TDC work out in your application? Like, well, I tried it and it diverged. Their methods are harder to use. They have two value functions they're learning at the same time, two step size parameters. There's variance due to importance sampling, so they're difficult to deal with. And so we need more practical experience with them. And they're basically unexplored with nonlinear function approximation. Like, people have just not used these methods much with like neural networks. And then there's a yet newer family of methods called retrace from Remy Munoz' group at DeepMind and its successor vtrace and the ABQ algorithm. And you can think about these methods as adapting the corrections online to keep things stable. And so they're based on things that are outside the scope of this lecture, but they work very, very nicely. They have convergence results in the tabular case, and they work really, really well. So Remy's used them in large deep learning systems. They work really nicely. They improve performance, but technically they can diverge, and we need to extend them to make them more robust for those situations. And of course, Hadovan Hassett and his group did a really nice study just analyzing the deadly triad in reinforcement learning with deep learning systems. And in fact, they looked at Q-learning, tried to look at all the different ways they could make it diverge. It's a really nice empirical paper about all these things. I encourage you to check it out. And it had some really interesting conclusions. So one of the obvious ones was if there's a big difference between the two policies, remember there's two policies, one we're learning about, one that's controlling the actions. If they're very, very different, then we can get divergence. And that's not super surprising, but it's important because it comes up all the time when we do prioritized experience replay, or if we do sample-based planning, which Martha's going to tell you about, or parallel learning. We often get these big differences between these policies. And also, one of the other surprising conclusions they found is that with bigger networks, you were more likely to diverge with DQN. And so this is interesting because they've done a big, beautiful empirical study, but it's also interesting because these are two things we really want to do in large-scale learning systems, like, again, kind of non-negotiable things that we want. And so Doina's going to talk a lot more about off-policy learning, and she's probably going to cover a lot of these things. So, I got a couple minutes to finish up here. Sorry, Cam. I just wanted to finish on both a positive and a note to try to get you to look at different things. And so, this is the laundry list of awesome applications we have in reinforced learning. Backgammon with Jerry Tesaro, Andrew Ng, Peter Beal, Coates' flying helicopters upside down. Those videos are absolutely amazing. They're hilarious and much better than any person can do it. A/B testing, Watson for daily double wagering used reinforcement learning. Obviously, DeepQN, obviously all the Go stuff has been really, really important successful applications, right? But if you notice, there's a trend here. There's one odd one out, which is the helicopters, right? The rest of it's in simulation. That's where a lot of our big successes have been. And that can be good, that can be bad. Simulations are great because they facilitate amazing empirical research. You can really test an idea very carefully. You can control things in just the right way and make beautiful scientific conclusions. We don't always do that, but that's the thing we want, right? But they're also bad because they allow us to cheat just a little bit, and we do cheat. So we do things like we run parallel copies of the environment. So, I just sit here and think about, copies of this room talking to you guys, 100 different copies, and I'm giving a lecture in each one of them in my mind. Okay, that's kind of hard to do. You can easily reset to states. Dying is just not a big deal. You know, if the agent destroys itself, doesn't matter, just start over. You can jump to anywhere in the world. You can ignore damage. You can use the knowledge of the environment, right? Like, think about it. Go, StarCraft, DeepQN, they have one-step dynamics functions. We know that. We're implicitly using that, but something like a robot, it's not clear at all with how the dynamics evolve. So we lose a little bit of focus on data efficiency, exploration, parameter sensitivity. You know, if we have a simulation, we can run hundreds of copies of the environment, and we can run it on a cluster for weeks and weeks and weeks. You know, maybe we don't care if our exploration algorithm is so good at exploring the world. Maybe we don't care that, you know, there's one parameter setting out of billions that actually works well and all the other ones fail, because we'll just let massive compute deal with that. You can't do these kind of things on robots. You can't do parameter sweeps on a robot. You actually have to care about how quickly things learn, how it explores the world, whether the robot drives off a cliff or not. That's relevant, because at the very least, you have to buy a new robot. So I think this is like a really open frontier for reinforcement learning research. It's something we need to work more and more. And there's tons of groups all over the world that are working on it. Berkeley, they're doing great work, and we just need to do more. And so, you know, part of the inspiration for Friday, we're going to have a whole sequence of talks on doing RL on robots, right? Jan Peters, Rupam, Patrick Pilarski, they're all going to be talking to you about robots and why it matters to do them with reinforcement learning. And so just to wrap up here, of course, you know, there's lots of things we've done in reinforcement learning. It's a very exciting time, but we also have to temper our excitement and realize, you know, we're not done. So this is, of course, is just poking fun at Montezuma's revenge and the even harder pitfall that we don't even talk about, because usually the systems just don't do anything in pitfall. Which makes sense, because if you play pitfall yourself, you do actions, and it's not clear at all how that's related to the score. So I can see why it's hard. But, you know, like I said before, our exploration methods are unsophisticated. We need to start talking more about planning and models and better use of exploration before we start making real progress on things. And we don't want to just overfit to these domains either, right? Solving pitfall or Montezuma's revenge itself doesn't matter. No one cares about those games. We care about having general techniques that come out of thinking about those games. And you know, we do have systems that can perform really well, but they're extremely sensitive to how we design them, right? We still have a lot of human in the loop to make reinforcement learning systems work well. So this is from Joel Pino's group, you know, showing that the architecture configuration and the activation units all make a huge difference in the performance of deep learning systems. And of course, you know, this video is Boston Dynamics, the best robot manufacturer in the world. They have excellent control policies. Right? This is not to say it's using reinforcement learning, but it is to say that they're using hand-designed policies, and it's really, really hard. And this is what we need to work on. Right? Like, that's horrible. That's terrible. And I could find 1,000 other videos like this for you. So we've talked about a lot of things today, and we haven't got into all the things I want to get to, and I went way over time, so it's clear that I already covered too much. But you know, there's so many things to think about in reinforcement learning. You have the whole week of learning about it in front of you. Prediction and control problems, MDPs, contextual bandits, and the simple bandit game we started with. And there are all kinds of things inside reinforcement learning. Bootstrapping that we talked about, Monte Carlo methods, eligibility traces, going from tabular to function approximation and dealing with partial observability. Lots of people are going to talk about that stuff this week. On-policy and off-policy learning, model-based reinforcement learning, value-based and policy-based. We don't just have to learn value functions. We can learn a parameterized policy as well. And then temporal abstraction, which is really fun. The idea that we don't have to just reason about the world in single time-step actions. We can think about the world in terms of, what if I executed this way of behaving for a while? Then I can learn even faster. And so we've put a lot of the pieces together already. We have really great algorithms. We've got lots of demonstrations of large-scale systems. Theory is always advancing really nicely. But there's just so much left to be done. It's a really exciting time to be in reinforcement learning. You just kind of stick your finger in the air and you'll touch an area that needs more work, needs more understanding. And so hopefully this week will kind of show you where the edges of all our understanding are, so that it can shape how you solve your own applications, and it can help you figure out where you might contribute to the field. So wrapping up, this is our RLAI group. There's a bunch of people missing from this this picture like Chaba, but he was in a different continent, but we'll Photoshop him in here somewhere as we usually do. We have a really large group here, and if you're interested and you want to come study with us, come join us. Thanks. Okay, well, you've asked a lot of questions, so does anyone else want to ask a question? You. That's good.
A lot of things can go wrong when you're training reinforcement learning. So how might you know the difference if you're like in a deadly triad situation or you're just setting up everything wrong and all your parameters are wrong?
So this is why Hutto's paper is really nice, because it's trying to show the space where the deadly triad comes up and when it doesn't come up in real learning systems. But usually the answer is your parameters or your function approximator. So either your function approximator isn't rich enough to represent the state, or you've set one of your many key performance parameters wrong. So if we're just doing epsilon greedy, epsilon, the learning rate, you might want to adapt the learning rate on a schedule. More advanced methods have bootstrapping parameters. Our systems have a lot of parameters. We have meta-learning algorithms that try to help us adapt those parameters, like the Atom Optimizer, AMS Grad, RMS Prop. They help us deal with the step size parameter, and they in general work pretty well. But it is true that for that one step size parameter, we've now replaced it with 3 other parameters that you can tune and get better performance. We usually don't, but you can improve. So it's probably parameters, but we're still in early days of becoming experts in making robust systems that people can just apply in industry.
Awesome. Thanks so much, Adam.